All right. All right, so let's start soon. So the people who are not sitting yet, please sit down. Okay. Hello. So not. Hello. If I can do this with Wordle, imagine the kind of lecture I can give if you only shut up. Okay. Okay. Hi everyone. Hello. So I want to finish up talking about the project. So I just want to give you two more techniques. And I also want to talk a little bit about the complexity connection, and then we'll do another sorting example. So first of all, so like you had a bunch of string stuff yesterday as well. So I think you're about ready to do everything, but I do want to show you a few more string functions that are useful. So one string function that's super useful is replace. So you can say, I am majoring in arrow. And then you can replace arrow with mi, for example, if you want, and that would replace every instance of arrow with mi. So this would be, again, a string, but every instance of arrow would be replaced with mi. So in fact, if you say like arrow is the best, it's just a string. It's not necessarily true, but so like every instance of this is going to be replaced. So that is useful if, for example, you have so if you have for example, commas and you have periods and you just want to replace all the punctuation with just the one thing, so that you don't actually want to split on the comma, but if you want to separate it into sentences, you want to split on both question marks and periods and stuff like that, you can just replace all the question marks with periods. All right. So that is like that. So the example would be, so you can do like replace. So that's so here, like MSF is still going to be like this, but you can also do like take this string, which still have MSF, and then replace MSF with MI as well, right? Like so. And that would first replace all arrow with MI and then replace all MSF with MI, and that ends up just substituting both arrow and MSF with MI. You can, of course, make a function like that as well. There technically is a built-in function that's like that as well, but we're not encouraging you to use it. So that is one thing. So the other thing, which you probably have seen by now, is split. So you can split any string like this. So if you say dot split and you say split on the exclamation point, what that does is it gives you a list of strings where the separator goes away, and everything that's separated by the separator is an individual element. Make sense? So we've already seen dot lower like very briefly, but dot lower converts everything to lowercase, like so. And finally, we haven't done sets. So sets are like lists, but every element is unique. So the use of that is if I have repeating elements in the list, like so, this is a list. If I convert it to a set, it becomes like this. So sets are written with curly braces like dictionaries are, but there's no columns. So that's a set like this. So all that we are doing is we're just saying, you know, if you say for E in set L, what it's going to do is it's going to give you one element at a time, and it's not going to repeat. So if I print E here, that's just going to print in some order, not necessarily sorted. It's going to print all the elements of L, but every element is just going to get printed the once. So that would be useful in the project. So coming back to what we're trying to do. So what we're trying to do is we're trying to build a descriptor for every word that kind of looks like this, right? The descriptor is I occurs, well, with the word man, I occurs 3 times. So 3 sentences where I and man occur, and then 3 where man and am occur, and 1 where man and sick occur, and so on. So there is actually a complexity element to this, because the straightforward way in which most people, I think, would start doing this is going to be impossibly slow. So one way to try to construct those things is to say, okay, so I have all my possible words. And that would be like whatever, like A is the first word, and then like whatever, aardvark, I know how to spell it, like this probably. Like this, and then like eventually like whatever, like zebra, I know what's like the classic last word in the dictionary is, possibly like ZZZ if that's a word, then yeah. Okay, and then you might say, okay, I need to know how many times each word occurs with every other word. How would you do that? Well, you might consider saying, you know, for W1 in words, for W2 in words, and then like something like counts W1, W2, you would have to set it up first, is equal to something. This is not real code. This is just like the plan. This is a terrible plan. The reason this is a terrible plan is that if you have 20,000 words, which is about what you have, this is going to take 20,000 squared, so 400 million iterations. that is a lot. In terms of asymptotic complexity, we would say this is O of n squared, where n is the number of unique words in the text. It's just not going to work. It's not going to finish running before the deadline for submitting project 3. If you do it like that, technically it doesn't need to. Like when you submit the code, you don't need to run it. And we are not testing it with the novels. We're testing it with small examples where it will finish running. However, we are also testing it for speed. And we are making sure that you are not doing O of n squared, which is disallowed. So what can you do so that the complexity is kind of linear? Well, what you can do is think about it like that. So you have this kind of text. So maybe it's like this. And then what you would do, so I'm just copying and pasting the Dostoevsky, right? So what you can do is you can say, okay, all right, so I'm going to go one sentence at a time. And I'm going to say, okay, like, let's say that I have my counts. And I'm just going to update the counts by looking at this sentence. This sentence gives me information that says I and M occur the ones. And then I and Sig occur the ones, and so on. So I just look at every pair in the sentence, which is necessarily short. It's just a sentence, and update the counts that way. And then I go to the next sentence. And again, I update the counts by looking at the pairs of the words inside this sentence. And then I do it for the third sentence and so on. Okay, so the plan all right. So what is the complexity of that going to be? So first, I'll write out the plan, and then we'll see how it goes, right? So I'll say something like for sentence and sentences. So there is a function that makes you do the sentences, stuff like that, right? And now what I'm going to do is I'm going to say, okay, so for W1 in sentence, for W2 in sentence, cannot spell today. And again, I'll update counts W1, W2. So that looks like it's even worse, but it's not, right? So the reason it's not is that if the maximum number of words per sentence is whatever K, I don't know what K is, but it's something. And then like the number of sentences is N, then the complexity is O of N times K squared. Right? So that looks, well, I don't know if it's worse or better, except if I know the details about the language. So if I know that in the English language, sentences are not more than 200 words, then I'm going to say it doesn't matter. Like the K square, it's like 200 squared, it's a constant. So even if I have a very long corpus, the runtime is going to be proportional to the number of sentences, not to the square number of the number of words. The square of the number of words is 400 million or whatever it is. That's a lot. This is the number of sentences, which is large, but not 400 million. So that is going to finish running in seconds or like tens of seconds if you do it right. On the other hand, that strategy just does not work. All right. Questions about this? Does this not make sense? Well, people are nodding. It's but that was like a grammatically complicated question, so I don't know. So okay, all right. So hopefully that gives you a plan. You are now ready to do project one. So get going. I think it's a fun project. Let me kind of just briefly, someone asked me about it after lecture because I guess they like stalked me on LinkedIn or something. So we just published a paper. I just do Wordle. So we just published a paper that kind of has to do with what we were talking about just yesterday. So I'll spend like 2 minutes talking about it. So basically what we did is we scraped Reddit for kind of games that people posted, Wordle games that people posted on Reddit. And what we're looking at is, are people playing suboptimally? And can you predict in which way they're playing suboptimally by saying, well, people probably keep guessing words that have similar meanings to each other just because they're primed to do that. So priming in psychology means that if you saw something before, you're kind of inclined to repeat the kind of thing that you saw before. So similarly, we're interested in whether people play words that rhyme with previous guesses. They kind of do. So that's like the phonological bias. And also if people tend to repeat letters more than usual, which is like the orthographic bias, not words, sorry, letters. So the semantic bias is basically using the technique that we discussed last time, which is word vectors. So in order to figure out whether people play similar words, what we do is we just compare the word vectors for the guesses that people make. And we ask, are the word vectors closer together than what you would expect if people were just playing optimally? And the answer is yes, not always. So you got to separate out the thing into where people don't have a lot of choice about what to play. So if there's like 4 green already, then the bias is not really pronounced. But if everything's gray, you do see this bias a lot. So people keep guessing words that are related, presumably because they're either lazy or they're like subconsciously primed to do that. So yeah, that's our paper. So okay, advancing science, one Wordle guess at a time. So okay, all right, yes. I do that too sometimes. But yeah, like if you completely spam, then you would ruin our results. Luckily, not everyone is like you, so that's why we managed to publish, is some people are not just spamming. So okay, and maybe if everyone was not like you, we would have gotten into a better journal because the results would be stronger. So well, like Wordle is just 2,000 words, so like that's completely fixable in terms of bad vocabulary. So okay, so I should say 2,000 valid guesses, and then 2,000 things that would be ever an answer, and 10,000 valid guesses. Enough about Wordle. So okay, all right. Yeah, and those, by the way, so Adam is a TA in the course. Gary used to be a TA in the course. He's now on PY. Kina graduated, but those are all size. So yeah. Okay, all right. So I want to do one more sorting algorithm. Then we'll stop doing sorting for a while in order to do a technique that we need in order to do the actual serious sort. So far, the sorts that we had were O of n squared. So selection sorts, bubble sorts, where n is length of L, right? So that's kind of slow. So can we do better? the answer is 1, yes. 2, in some situations, you can do a lot better. So here's an idea. Let's say that I'm just sorting integers. So L is, 2, 1, 100, 2. And we'll make them positive. You can fix that pretty easily, but we'll make them positive. So the idea is like this. Instead of rearranging the elements, I'll just say, okay, so what do we have here? We have 3 2s, and we have 1 1, and we have 1 100, and we have 1 500, and we have 1 1200. From that, I can kind of read off the sorted list, right? So the sorted list is 1, and then 2, 2, 2, and then 100, and then 500, and then 1200. All right. So that's the insight. So what I want to do is I want to set up a list counts which will contain the number of times each element appears in the list. And then read off the sorted list from that. This is known as counting sort. You might have heard of the term bucket sort, which is kind of a more general version of that. So I'll call it counting sort. So, okay. So what do I got to do here? I got to set up the counts list. So if counts is a list, so how large should it be? Like I need to know like how many zeros, how many ones, how many twos, and so on, up to the max of L, right? So that is going to be 0 times, so this is just the length of the list, max of L plus 1. So that is so I can have count 0 and counts 1 and so on, and counts max of L. So that way I have information about how many times each possible element in the list L appears. Does that make sense? So, okay. So now that I have that, all I got to do is I got to go through the list and increment the counts every time that I see an element. So I'll say for E in L, counts at E plus equals 1. So at the end, I'll have something like this. And now I got to build up my my solution. So let's do something with smaller numbers so that we can see what's going on. So let's say that we have like 5, 1, 1, 1, 3 or something. That's the list. So counts then will be what? So there is no zeros. There's 3 ones. There is 1 3. There is no 4s, and there is 1 5. Does that make sense? So here I'll just write the indices. So this is 0, 1, 2, 3, 4, 5. Make sense? So, okay. So how then do we build up the answer? Well, we start with the empty list. Then we say no zero, so there's nothing to do there. And now we need to extend it by 3 ones. There's no 2s, there's 1 3, there's no 4s, and there's 1 5. So the way we'll do it is we'll say, okay, so for I in range length counts, we'll say extend the result. This is a little bit subtle. So we want to add I, possibly 1, possibly none. How many in general counts I? Right? So if count 0 is just 0, so that's just going to be nothing. Counts 1 is 3. So this is going to be the list 1 times 3, which means this kind of deal. And we're just extending it, which means that we are, adding 3 ones to the result. So that would be this part. And then we'll add the list 2 times 0, so nothing. And then we'll add the list 3 times 1, so 3. And then we'll add the list 5 times 1, so 5. Make sense? So we're done. And we are returning result. Questions? Does this make sense? Does not make sense. All right. Let's now do the computational complexity of counting sort. So before, when we said, like, what's the computational complexity, we said, well, like, in terms of the input of the size of the input L. Here we have 2 things that are going on. So we have the size of the list L, but we also have the maximal element of L, M. And that matters because the length of counts is not actually to do with the length of L, it's to do with the maximum of L, right? So we'll say in terms of the maximum and the length. There's 2 things that are going on, right? So, okay. So at this point, what we got to do is we got to actually say, okay, how long does each line take? So this line, it looks like it's 1 line, but actually in order to construct a list that's of size max of L, you got to spend time that's proportional to max of L, because like you got to put 0, 0, 0, 0, 0, M plus 1 times. Right? So I don't know how long it's going to take exactly, but it's going to be C1 times M for some kind of constant C1. So I'll write it as this takes C1 times M time. Does that make sense? So how long does this take? This is just proportional to the length of the list L, right? Because we are repeating just plus 1 length of L times. So this is going to take C2 times N time, where N is the length of the list L. Now, this is the really tricky part, because you might say, well, this takes time that's proportional to M, to the max of L, but you would not be quite right. Because it's not the case here that each one of those takes the same amount of time, right? Why is it not the case that line 31 takes the same amount of time every time? Anyone? Yeah.
And on like
Yeah, it depends on count psi. Exactly. If count psi is 0, it doesn't take anything. If count psi is a bajillion, then it's gonna take time that's proportional to bajillion. Right? So how do we approach this? Well, there is a trick. So we'll say, I don't know how many things I append to res at every given iteration, but I know how many things I append to res in total. How many elements are going to get appended to res in total after I finish running the loop? Anyone? Yeah. Yeah. How many guys first row? I see you're having a spirited discussion, probably actually about the course content, but it's distracting. Sorry. So how many times, how many elements are appended to res in total? Anyone? At the end. So we start with a list L, and res at the end is the sorted L. So how many elements are appended to res? Yes. N, yes, because it's the same as the list L, it's just sorted, right? So we don't know how many at any given point, but in total, we are appending N elements to res. So also in total, this loop runs M times, technically M plus 1. Right? So what we can say is, okay, so this line takes time that's C3 times M, because just running the machinery of the loop takes something that's proportional to M. And then line 31 in total takes C4 times N times, because what we're doing is we're building up a list that's of length N. In total, that's going to take time that's proportional to N. So the total runtime is going to be C1 plus C3 times M plus C2 plus C4 times N. So if we don't know either N or M, we would say that the complexity is O of N plus M. And that's just because like we drop the coefficients, we don't know what they are anyways. If you know that M is limited, so for example, if you know that your integers are not larger than 1 million, then it's a constant, and this sort is linear time, if you consider M to be a constant. Of course, if you don't know that your integers are limited, this could potentially be huge. Potentially, if your integers are so large that the list counts doesn't even fit in your computer memory, which, it easily could. You do not have, 10 to the 500, you don't have 10 to the 500 memory cells in your computer, but the maximum of the list could easily be 10 to the 500. It's just one with 500 zeros at the end. It's not hard to store. So this could take a long time. It could not, but if M is limited, then it's linear. Yes.
Why is this line C1 and N So like I thought it was like you go through the list to find the
Oh, you're right. So it's thank you. So C1 times M was to construct this, but it would also take C5 plus N to find max of L. You're completely right, and we'll add the C5 over here. Well, I mean, like, if you think about it, like, in order to write a zero, it takes some amount of time to just like to write the zero to some location in memory. If you got to write 500 million of those zeros, that's going to take time that's proportional to how many zeros you're writing. Yeah. Okay, but your point is well taken. So I kind of ignored how long it takes to actually compute max of L. In order to compute max of L, you got to look at every element of L. So that's going to be proportional to the size of the list L. All right. Okay. Does the analysis make sense? Questions? So this is not supposed to be like an easy analysis. It's probably one of the more complicated analysis that is not an analysis of recursive functions. As you see, you like so one you have to well, so I kind of forgot about max of L. So you have to like see, okay, like this is proportional to this is proportional to that, stuff like that. And then here you just had to use a trick where you had to figure out how many times this runs in total. In addition, because it's Python, technically, I just hand waved and said, okay, like max of L is going to take time proportional to L. You don't know, right? You don't know what Python does inside. On the exam, we are not going to use max of L or anything like that, just because we don't want you to make like assumptions about what built-in functions do. So if you look at past questions on the exam, they do not have this kind of thing, unless it's like specifically something that's like counting sorts where you're supposed to know, but there's not going to be like new stuff where mystery Python function. Just imagine what the complexity of it is, like what's the runtime proportional to. With that said, with max, well, it's got to be proportional to N, just because, well, like in order to find the maximum of a list, you got to look at every element once, and you also don't need to look at every element more than once. So it's proportional to the size of the list, because it's just a simple for loop to actually do this manually. All right. Does this make sense? Questions? I think the other difficulty that people usually have is with the O of N plus M, which is an unusual thing. Usually you would say the complexity is like O of N or of N squared or something like that. But here it generally depends both on N and on M. So if the runtime is something like this, where it's like some unknown constant times M plus some unknown constant times N, just simplify it to M plus N. All right. Questions about this? All right. I do not think so. We are about to start recursion, but we have 9 minutes left, and that seems like not a good time. So what I'll do instead is I'll do one more example that was actually promised last lecture, and then I will let you go. So this is just like another example of computing complexity. So, and I think it appeared on one of the exams. So, okay. So let's say that, hey, it's an example that could be on the exam. Yeah. So let's say that I do something like this. It's going to be a function. All right. Do you guys know the answer? It's hard. All right. I guess not. Okay. All right. So first of all, kind of. So what are we counting here? Well, there is an inner loop here, so we're just counting how many times does the inner loop run. I didn't initialize I. It's supposed to be 1. All right. So how many times? The answer is, well, like it's a variable number of times. Like the first time it runs the once, and then twice, and then 4 times, and so on, right? So it's 1 plus 2 plus 4 plus 8, and so on, plus approximately n, right? And that's because, sorry, and that's because I grows by 2 every time, and we run I times, right? So the question is how much this is. All right. So in order to do that, we need one more formula. That is the sum of the geometric series. So 1 plus r to the 1 plus r squared plus r cubed, and so on. Plus r to the k is equal to 1 minus r to the k divided by 1 minus r. Ring a bell? If not, now you know. So now we got to actually apply this formula to this, which is not that straightforward because we need to transform it again. So this is equal to 2 to the, so 1 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3, and so on, plus n. But what is n? Well, n is just n. So what we'll do is we'll do a substitution. So the substitution would be n is equal to 2 to the m for some m. And then what is m? Well, if you take the log of both sides, m is going to be what? Log to n. Someone said it. So this would be equal to this much, with 2 to the power of log to n. Make sense? And that makes sense because like 2 to the power of log to n, it's like, you know, like what power do you need to raise 2 to in order to get n? It's like it's n. Okay? But now we can apply the formula. So this would be equal to 1 minus 2 to the power of log to n divided by 1 minus 2, which is just minus 1. And that would be equal to this, by the way, escape this one. And this would be equal to 2 to the power of log 2n, which is n minus 1. Sorry, this was k plus 1, of course. So this would be 2 to the power of log 2n plus 1 divided by 1. 2 to the power of log 2n plus 1 is equal to 2n. Okay, so this is just using the properties of powers. So 2 to the power of w plus 1 is equal to 2 times 2 to the w. Make sense? So that means that this thing is equal to 2n minus 1, which means that because of this, which means that the answer is all of n. Right? So that was kind of the intermediate case. If you remember, we said it's kind of difficult to do a nested loop where it's not O of n and it's not O of n squared. And here what you see is it is a nested loop, but the issue is that the I grows so fast that what's really important there is that when I is large, it's proportional to n. Everything else is just small change. Say it. I mean, the while loop runs log to n times, but no, because this is sorry, guys. So that was a really good question, which I want to answer. So the question was like the while loop, how many times does that run? Well, that's log to n, right? But what we really are counting is how many times this runs, because it's not like how many times this runs times how many times this runs, because this runs a variable number of times. So we're just counting up, okay, this runs once and then twice and then 4 times and so on. That includes this stuff anyways. Yeah. All right. Okay. Have a good weekend. I'm done. See ya. Bye. Dan? No, that's just like a regular latte. Yeah. I'm sure. Yeah.
I guess just the lab thing still happening at 6 a.m.
Yeah.
So I can show you my lab and get it rated.
Like if you miss the lab, then there is like a piazza thing where you can just make an appointment with Bill. So like the lab is like a session where I solve the lab. It's not where I check anything.
So I just show you it or?
So like can you like just email Bill and yeah.
Okay.
Yeah. Yeah. Yeah.
So if we consider that while loop is can be proportional to time long to
No, that it's fewer than that because there's like no, this is not n, right? This is I. So when I is equal to 1, this just runs 1. And then when I is equal to 2, it runs twice. When it's 4 times, it's so on.
Oh.
So it's not like this times this.
So
And we couldn't, like, there is no times this because this is I. It's not like a constant outside of it. So for that reason, we have to say, okay, like, we're just kind of manually count how many times it's coming.
Okay.
And the answer is like 1 plus 2 plus 4 plus 8 plus n. And then we figured out that that actually is equal to 2n.
Okay. Thanks. So this kind of for the whole thing common time.
Yeah.
Also, like just during the exam, we will get the formula for this, right?
No,
No.
no. So two formulas that you need to remember is the geometric series and the arithmetic series. Got to memorize it at some point. Might as well be now.
Okay.
Yeah.
Yeah, thanks.
Yeah.
Now, if that's the case, what is like just in the exam, I cannot forget the formula and I use my own logic to make an estimate and still use similar log to and stuff like that. I also got partial mark.
Just remember the formula. So sometimes what you'll see is that like because kind of grading this kind of derivation is annoying, we just ask for the final answer and then we ask for a justification. But we don't really give you any points if the answer is wrong.
Oh,
So sometimes we kind of grade the justification as well, in which case, of course, but a lot of the time we just ask like kind of like a multiple choice kind of thing. Not exactly multiple choice, but we kind of ask for the final answer. And then we say, if you don't justify it, you don't get any marks. Or if your justification is completely off, but also if you don't get the answer right, you don't get any marks. And that's just because like if it's off, it's really difficult to grade. Like
Yeah.
there's kind of no point. Yeah.
thanks.